When you draw a Lewis structure, it's not always a perfect model for a molecule that you may be looking at. A good example of this is residence in Lewis structures. So some molecules, because they have a double bond, there's no one way to draw the molecule. You actually need to draw two or maybe three molecules to represent what is going on in that one molecule. The actual structure is a blend of the Lewis structures that you can draw. It's because of the limitations in the Lewis structure. So let's look at resonance. So in resonance, we have molecules that can't be drawn with just one Lewis structure. And again, the actual structure is an average of all the possibilities. You will always see a double-headed arrow between the resonance structure. So down here we have the molecule ozone, it's O3. So on the left-hand side, I have a double bond on the left-hand side of the molecule, and then on the right-hand side, I have a double bond on the right-hand side of the molecule. Well, which one is it? Is it on the left-hand side or the right-hand side? So the molecule is actually moving those electrons around. When you go to look at the bond length in the ozone molecule, we find that it's not a single or a double bond, it's kind of a blend between the two. So how you draw this is to draw a double bond on one side, a single bond on the other, and then connect the two molecules that you draw, the two resonance structures you draw, with that double arrow. When they actually go to look at the bond length, they find that it's equal. And so the electron in that bond is going back and forth between both of the bond areas. So let's draw the resonance structures for nitrate ion. So nitrate ion, it is a negative ion, and so when you draw the Lewis structure, you need to encase it in these brackets, and then you'll put the charge of the ion right outside the bracket. So what that is telling us is that we have one more electron in there. So when you go to count valence electrons, you'll count the valence electrons, but you'll also have to add one more because this is an ion. Now looking at this, we have a double bond right here on the left hand side. Well, how come we didn't put it on the top? And the answer is you could have. And so let's draw a resonance structure. So we have nitrogen in the middle, our double bond going up, and then we have our oxygens. And I'm going to quickly put the dots in. So you see that all the elements in this structure, they all have a full octet. And I can't forget to put in the charge of my nitrate. It's that little negative sign. I actually can draw one more because why couldn't I put that double bond on the right hand side? And the answer is you can. So when you look at the Lewis structure of nitrate and you look at that bond length, you find that it's actually about the size of 1 1/3 bonds. So again, you have some moving of the electrons in that double bond around the molecule. So it might be on the left-hand side going up or on the right-hand side. But these are the three resonance structures of nitrate. So just one doesn't represent what's going on with the molecule. You actually do need to draw all three of them. The actual structure of the molecule is a blend of all of these. Now let's turn to a different topic, and it is isomers. So in isomers, that's when we have the same formula, but we have a different molecule. And that is because it's bonded together differently and it will have different chemical properties. Let's first look at different ways that we can draw these carbon and hydrogen compounds. So looking at C4H10, I can represent the formula like this, but it doesn't really explain how it's bonded. So we can draw it out. So this is just drawing the symbol of the element and then connecting it with a line, the skeletal structure. It's kind of a pain to draw all those carbons and hydrogens and bonds. You also could represent it like this, saying that, hey, in that first carbon, I have 3 hydrogens bonded to it. In that second carbon, I have 2 hydrogens bonded to it. And then here's a real shortcut way, and this is a line drawing. So every time you have the end of a line or an elbow, that represents a carbon. So you can count your carbons. 1, 2, 3, 4. So this is C4, and that it is assumed that every carbon will have 4 bonds on it, And then if it doesn't tell you what you're bonding to it, it will be hydrogen. So this is also C4H10, but just a quick way to draw that. Now look at the bottom of the screen. We have two isomers. These are both C4H10. I have just a carbon chain, so I just take my carbons and I connect all the carbons together and I make sure every carbon has 4 bonds and so draw those hydrogens around. Then to get this next one, you cut off this last carbon and you're going to trade it with this hydrogen. So they'll switch places. So in this way, you have the carbons bonded a different way. The first one, they're bonded in a row. The second one, we have 3 bonded together, and then we have 1 bonded on the middle carbon. It's really important that when you take the carbon off, you put it on a middle carbon. If you just connect it to the other end, you'll end up with the same thing. There are different types of isomers. So on this first one, this shows a fluorine atom, and here, or excuse me, a chlorine atom, and it's down here at the end, and then here it's on a middle carbon. So these are two completely different molecules with different properties. You also could have a double bond move around. So here it's between the first 2 carbons, and here it's between the second and third carbons. Again, these have the same formula, but you can draw them differently. So it's different than resonance. So in resonance, you have one molecule, but you can't represent it with one Lewis structure. You have to draw many. Isomers mean you have the same formula, but there's many different ways to connect the atoms together. And in this type of isomer, we separate the carbon chain. So in the first picture, we have our carbon chain, our carbons are together, and then we have an oxygen. And then the second one, we have that oxygen interrupting the carbon chain. And so this creates very many different changes in physical properties. So the first one is an alcohol, so it's going to have an alcohol smell. The second one is an ether. It'll have a completely different smell. Interestingly enough, they both are quite aromatic compounds. And we can even have mirror images. So we can have molecules that they look the same if you put them in a mirror, but they are actually completely different molecules. Because there's a left-hand side and a right-hand side, these are often called left and right-hand isomers. They're also called chiral centers or chiral carbons, meaning handedness, and we can get totally different reactions to each of these. In medicine, optical isomers are very, very important. If you generate a drug that has an optical isomer, you possibly could have problems with it because the body might interpret it different ways. There's a In the 1950s and or 60s, there was a drug called thalidomide that happened to have this chirality or this optical isomers, and one helped the pregnant woman with her morning sickness, and the other one actually caused birth defects if it was taken at a certain time. So this happened over in Europe, and we didn't really see it in America because America decided to not release this and let pregnant women take it until further studies were done. And it turned out quite disastrous in Europe with a lot of birth defects, and America was able to avoid that because they were so cautious.